this computer. Okay, so it should be recording now. And I think maybe a couple more people might join, like Kavin and Reja. So I'll actually make you the host, Dr. Yi. If anyone joins the presentation, would you be available to add them to the room?
Sure, no problem.
Okay, thank you. Alrighty, sounds good. So can everyone see my screen okay?
Yes, we do.
Great. Alrighty, so I'll go ahead and hop in and get started here. So my name is Osaze Shears. I've been working with Dr. Yi's research lab, researching different types of neuromorphic computing and reservoir computing for about 2 years now. So I joined Virginia Tech as a master's student back in August 2020. And essentially, my research has been really focused on how we can combine a lot of the different neuromorphic computing techniques that we've been researching in her lab with some different wireless communication types of applications. The reason for this is because, as you know, 5G and wireless communications is becoming increasingly more popular because of 5G, right? So there's a lot of contemporary research that's looking into how we can merge this emerging field with a lot of these new ideas that we have to consider with some of the things that have been done historically with machine learning, such as hardware machine learning, and even more emerging approaches like spiking neural networks and stuff like that. So this presentation will cover one of these areas that attempts to merge these two fields, which is reservoir computing, which I'll explain more in depth during the presentation, with a concept called spectrum sensing, which allows us to do some pretty cool things with some emerging devices and managing frequency spectrums and things of that nature. So that's kind of just an overview before I get started, just for a little bit of context. And with that, I'll hop into it. So my presentation is named FPGA Reservoir Computing for Dynamic Spectrum Sensing. So here's a brief outline. I'll keep this outline kind of running as we go through, but first I'll start out by introducing some pretty fundamental basic concepts about machine learning on edge devices. So machine learning has gone through, it's a really big buzzword these days, and it's gone through a pretty interesting trajectory over the past 2 decades or so. I think that in this beginning phase, this pre-2010 area is when it was first getting its kind of foothold, its foundings, and a lot of different types of applications and things of that nature. So during this initial pre-2010 time, this is where GPUs were first applied to machine learning. And also one of the fundamental machine learning benchmarks was developed called ImageNet. And I think these two developments really kickstarted the idea for seeing how we can apply different types of machine learning models to perform a lot of cool things, such as image recognition. After this initial conception phase, we entered a tool refinement phase, from what I can tell. During this tool refinement phase, a lot of key applications were developed to ease the implementation of different machine learning algorithms and data processing. These include Apache Spark, which led the way for processing a lot of big data very efficiently. So it streamlined that process a decent amount. And TensorFlow, which is a very popular machine learning framework based in some C++, some Python, allows you to essentially create machine learning models very efficiently and apply them. So that really opened the doors for a lot of people to get involved with machine learning and take it out to even more advanced applications, which I think is the main focus of this next phase that I'd say we're currently in, where we're using machine learning models that have been developed with some of the tools that were developed earlier and seeing how we can increase the performance, the speed, the efficiency of these models for different applications. So Apple has been kind of one of the forefront runners of this implementation on the edge computing side of things. They released the A11 Bionic back in 2017, and this was their first system on chip that actually utilized a neural processing engine. So they had dedicated silicon, dedicated hardware in that SoC that was able to perform machine learning inference. Google has also done some of this with their tensor processing unit, and these are big, large-scale devices, kind of similar to GPUs in a way, that streamline the process of performing machine learning type calculations in cloud computing settings that require a lot of power, but also give you a lot of accuracy. We'll explore that in a moment. And then also another interesting development was the Waymo autonomous vehicle service. So this is like an autonomous taxi service that leverages these different types of machine learning hardwares to essentially provide people with this autonomous taxi service. And I think it launched in Austin, Texas. So these are only a couple handful of selections. There are plenty more that aren't covered here, but it kind of gives you an idea of the development of this machine learning technology that we've been through in the past few years and kind of where we're at right now. So there's pretty big focus right now on seeing how we can take all of these software models that have been developed in the past and incorporate them in hardware to improve their efficiency and performance. And that's key to what this research that I'll go through in this presentation kind of explores. So these are two examples of machine learning hardware architectures, specifically with regard to cloud computing. On the left side, this is the architecture for Google's Tensor Processing Unit, or the TPU. So oftentimes when you use a platform like Google Colab, which they've made very open and available, you can take advantage of this specialized hardware that allows you to improve the speed of inference and training for your different machine learning models. As you can see from the system architecture that's portrayed over here on the left, this uses a lot of large and parallel logic. So they have batch matrix multipliers, an array of these matrix multipliers, since that's a pretty frequent operation that's done for a machine learning task. In addition to a lot of different control logic and memory management logic that allows you to access the different weight values and the different outputs of various machine learning layers and neurons. So this is a pretty kind of typical architecture, and a lot of research papers have gone on to explore variations of this architecture. Alternatively, GPUs, as I mentioned on the previous slide, have been repurposed for this reason as well. So on the right side, you have a specialized GPU architecture. So this is NVIDIA's A100 GPU. And here they've incorporated not only the traditional GPU type of functionality where we have batches of different ALUs performing both integer and floating point arithmetic in parallel, but they've also gone on to include some specialized tensor cores which perform some of these neural network type operations that have been seen in Google's Tensor Processing Unit. So these two types of architectures have been pretty key in providing some advanced machine learning capabilities, specifically in cloud computing. And on the topic of cloud computing, we'll explore a little bit about some of the advantages that brings and some of the limitations that inspired the research presented here. So with cloud computing, it's very beneficial, and it really, I think, kickstarted the edge device computing revolution, because we could have these very small devices without a lot of power, or without even needing a lot of power or energy to run, because they're able to simply send data over a wireless network to the cloud. And these large cloud computing servers and systems are able to perform this machine learning inference and computation and send the results back to the edge devices. So the edge devices themselves, like cell phones, are able to have this complex capability without draining the cell phone battery instantly. And so some advantages of cloud computing, this approach, are data retention, because everything is stored in the cloud. If you lose your phone, you don't necessarily lose all the data that was on it. Adaptability, so this can adapt to a variety of different devices, and efficient devices because of that lower energy consumption that's required, since the heavy computation is happening in the cloud. However, the main limitations of this cloud computing approach are its latency, because when you have a device that's communicating with a server over the web, there's going to be some delay in getting the results back from that server. Bandwidth is also a major limitation because of the number of people that might be communicating with the cloud. It really constrains the amount of data that can be sent back and forth, and privacy as well, since the data isn't being stored on the actual device. Other people may have access to either see your data being transmitted over a wireless network, or if they gain access to the server, then the data can also be compromised in that way. Edge computing is an alternative to cloud computing. This approach kind of takes the limitations and turns them into advantages. So edge computing, if we're doing this actual computation on the device, then there's very little latency compared with communicating with the server. There aren't any bandwidth limits because all of the computation is happening on the device. And there's also increased privacy because of that as well. And so Apple's A15 Bionic, which is, I believe, their latest SoC, is an example of this type of edge computing machine learning that leverages all of these advantages relative to cloud computing. However, the limitations of edge computing are its area. Since we're actually having this computation happen on the device, then we don't have as much space to work with. The energy typically needs to be pretty low, or we need to have more efficient energy processing. So the power consumption needs to be kind of on the scale of 10 watts so that the battery isn't drained instantly. And also, since lower accuracy models are typically used in edge computing devices to decrease area, typically they're going to suffer from a reduction in accuracy as well. So these are some of the things that you trade off by having these advantages with edge computing. However, there are a lot of efforts that have shown different ways for maintaining the advantages of edge computing without sacrificing all of those things. So this paper at the very bottom that I linked, this summarizes these different optimizations that edge computing machine learning models can have. Smaller architectures, for example, is one of the focuses of these edge computing devices. Distributed training. So in this technique, we can separate the training to happen between both the server and the edge device. Model compression. So a lot of this focuses on quantization. So we take a model that might be represented by 32-bit floating point numbers or 32-bit integers and reduce that to 8 bits and see how that affects the accuracy. And also distributed inference. So having the actual identification or the actual object recognition task perform either on the device or on the server. So this essentially allows, if it's a more novice case where the phone isn't very confident in its prediction, it can ask the server what it thinks the prediction is, and it can get a more accurate answer that way. So these are some different optimizations that might be used to improve the performance of edge computing machine learning models. EfficientNet is a pretty good example of this as well. It records a pretty decent accuracy of 82% on this ImageNet classification task, which is a very challenging task because it has millions of images, and these millions of images are being classified into thousands of different classes. And it shows, compared to some state-of-the-art convolutional neural network approaches, an 8 times reduction in memory and a 6 times increase in inference speed. So these are all very good things and very promising for edge computing in general. And so given that we have a background now, we can jump into reservoir computing, which is a little bit of a different approach for this machine learning type of systems, and see how we actually apply that for our wireless communications applications here. So before we get into reservoir computing, it's important to first introduce recurrent neural networks, since this is a whole different new class of neural networks that, instead of processing data based on frames or fixed time periods, it's actually processing data over time. So a popular recurrent neural network, which is a time-based neural network, that's often referenced as the long short-term memory, or LSTM. This is essentially a network that incorporates this idea of short-term memory. So as you read data over time, the network will either store that information and use it to apply it to different inferences or calculations. This on the right side is an example of what a long short-term memory cell might look like, which are the building blocks of this LSTM network. So these are often arranged, as you would imagine, a typical neural network with different layers in a very similar way to that. And essentially how this LSTM cell works is that there are different gates here that allow it to store data, to modify the data that is stored, or to output data from the actual cell. And these essentially allow it to perform regression or classification types of predictions on whatever data set that you're using. So that's the idea behind this. And so these have been demonstrated on some time series based applications such as speech recognition, text generation, those different applications that are going to incorporate time as opposed to being a static image, for example. And so how these different in terms of their training from traditional neural networks like convolutional neural networks is their backpropagation is happening over time. So instead of performing all of the weight updates at one period in time, you would consider multiple different time steps as you're performing those different weight optimizations, which is the process of training this neural network. Another approach, which very similar to LSTM, but a little simpler and has been demonstrated for other applications as well, is the gated recurrent units. So these pretty much go hand in hand. The architectures are very similar. The GRU is just a little bit simpler in terms of how it works. And so that's kind of the most popular initial ways that we use neural networks for training them on time series data. But back in 2001, a researcher, Jaeger, proposed a slightly different approach for performing these time-based neural network calculations or predictions. And this approach was called the echo state network. The main idea behind this is that instead of having these complex LSTM cells, we're instead using pretty similar cells to as you would see in a artificial neural network. The difference is that these neurons would be randomly connected, and the only training that happens in this network would happen at the readout layer. So the Jaeger's idea behind this was by only training the readout layer and allowing the actual reservoir, which this is called here, the reservoir of neurons, to learn the connections and form the feedback and short-term memory in the network, we can get pretty comparable accuracy to some of the more complex approaches. So how this has been tested is on a data set, which I'll show later on. And they actually found that, with this approach, it shows pretty similar performance while being much simpler in terms of its architecture and the process for training it, since only training happens at the output layer. In addition to the echo state network, another popular reservoir computing approach is the liquid state machine. And this is another alternative. It just uses spiking neurons instead of these artificial neurons. And there are other benefits that come with that approach as well. But these are kind of the basic ideas behind reservoir computing. And so researchers in previous works, more recent works, have demonstrated the ability of these reservoir computers to be applied to a lot of different tasks. So T-digits, which is a spoken digit classification task where we have a user that's saying either a number 0, 1, 2, 3, 4, or 5. What happens in that data set is that those words are spoken and the network is in charge of determining what digit was actually spoken. And with that particular application, this study found that they were able to get, with an echo state network approach, a error rate of 5%, which is pretty decent. So 95% of the time, the network was able to determine which digit was actually spoken. And they've also applied this for a human activity recognition task as well, wherein a user was having a smartphone or a wrist-worn accelerometer that, while they were performing some different types of actions like walking upstairs or brushing their teeth, and they used the echo state network to actually perform that inference to determine what they were doing. And so this is an example of the architecture for that echo state network that they applied in hardware. I won't go too into detail with all of the different optimizations here, but it's interesting to see how exactly they compose this, because a number of different optimizations are used here to reduce the complexity of the network in hardware. And by doing this, they're able to get pretty efficient neural network in a very low area with pretty high accuracy, as shown on the left. So relative to some of those earlier approaches like GRU, they saw a 60% area reduction and a 97% less power that was needed to be used in that process of classification. So just to summarize the advantages between the traditional approaches of LSTMs and GRUs versus these more lesser known approaches of reservoir computing essentially allows us simpler training, since training only happens at the output layer. There are fewer nonlinear transformations due to the absence of all those different types of gates, like the forget gate and the remember and the input gate, output gate. And the liquid state machine, just briefly, that could potentially have more energy efficiency because it's using spiking neurons instead of artificial neurons as well. Those are the main advantages of reservoir computing. However, the trade-off is that because we don't have as much control over the specific architecture inside of it, since they're more or less randomly connected to form the reservoir, it's usually going to have lower predictive performance than backpropagation training techniques shown with the LSTMs. So that brings us over to LSTMs, which generally they resolve some of the issues that were first proposed with these recurrent neural network approaches, such as the exploding and vanishing gradient issues, and they achieve state-of-the-art accuracy. But alternatively, the backpropagation through time that's required to train them is a lot more complex to implement in hardware compared to, just training the output layer. So an approach that looks at the reservoir computing approach and attempts to optimize it even more, which is the focus of this research, is the delayed feedback reservoir. So what this model does differently from the echo state network that was proposed earlier is that it eliminates a lot of those different neurons that were found inside, the artificial neurons that were inside of the reservoir, and it replaces it with only one artificial neuron. So this is essentially something like a time multiplex neural network, where we have input that's entering this delay loop of neurons. And over time, as the input gets delayed, that input will be factored into the calculation of future inputs. So essentially, I think one of the best papers that kind of visualize this delayed feedback reservoir, I'll show in the next slide, but essentially this can be visualized as a type of rolled up neural network. So we delay the inputs over time, and later on, we use those and factor it into the actual computation of future outputs, essentially. So the delay feedback reservoir is made up these N neurons that make up the delay loop. Training, just like the ESN, only happens at the output layer. And this work by Appleton actually showed that this DFR, with its simpler architecture, was able to achieve pretty similar accuracy to ESNs for some simple moving average prediction time series calculations. And oftentimes how people go about implementing this reservoir of neurons, it's very popular for them to explore this in both electronic and photonic approaches as well. So a lot of different approaches have been studied to see how this reservoir can be implemented. And so this is an architecture that a recently published paper that kind of moves forward this idea of the single neuron architecture with this time multiplexing. Essentially, the idea here is that, and this is just another way to visualize this, is that we can have these neurons that affect the outputs of neurons later down the road in the future. And what this can be visualized as at the very bottom is this unrolled network. So this is much more similar to a conventional neural network architecture that you might see. And here they've actually visualized how those different feedback connections can be unrolled to form a conventional neural network. And so in this paper, it's pretty significant because they show that with this single neuron approach, a network that only has one true artificial neuron, they're able to get pretty competitive accuracy for some common machine learning benchmarks like MNIST, which is a digit recognition data set, and CFAR10, which classifies thousands of different images into one of 10 different classes. So now that we've introduced this reservoir computing, we'll explore how these types of things can be applied to wireless communications, and then we'll dive into how exactly we did that in this research for this work. So just to introduce the problem of 5G and Internet of Things and kind of the premise that it provides. Currently, there are a lot of devices that are being connected to the internet, right? And by 2023, we're expecting to be 30 billion devices that will be connected. So this is a common report that's cited in a lot of different wireless communications papers, because Cisco is, one of the forerunners of research and development and wireless communications. So this is kind of seen as like the best guide for knowing at what scale connectivity will be in the future. So this figure on the right kind of highlights the increase of those devices. And if you look closely, you can see that the majority of this, the primary thing that's resulting in this increase of devices is this M2M. Over time, everything seems to be relatively the same, but M2M connections are primarily contributing to this growth of devices. And what this stands for is machine-to-machine communication. So it's talking about devices that are connecting or communicating directly with one another. So say, for instance, your cell phone directly communicating with your smart house or your car, right? So these are the primary things that are going to be increasing the number of communications, and that's happening over different wireless communications. And that's one of the main challenges that 5G is seeking to address, because we have a lot of these IoT M2M connections that are happening. So in terms of how we need to manage those connections is one of the main challenges, right? And so one of the ways that is being proposed to essentially manage these different connections is to offload some of these communications using spectrum sharing. So the idea behind spectrum sharing, it's a little bit shown in the bottom right, is to have devices not necessarily communicate through one managing base station, which is often used in a cellular communication type of connection, but instead have those devices communicate directly with one another. So on the bottom right, this is kind of visualizing the spectrum, radio frequency spectrum, for example. So there are a lot of different protocols that are being used, a lot of different devices that are communicating, like TVs, radios. And what you can imagine is that at certain frequencies in the spectrum over time, you have things like police communications or emergency responders that are using a specific frequency to communicate, but they're not always using that particular part of the spectrum. So essentially, there are going to be holes in the spectrum where nothing is really communicating over that particular frequency, but it cannot be used by other devices because it's, seen as a reserved frequency. So if something else is communicating there, then they might essentially, affect the ability of those first responders to communicate with one another. So spectrum sharing is the idea for, it's essentially an idea that's saying, okay, maybe we can have the devices be a little bit smarter about this interference and avoid interfering with those, emergency responders, for example, by first checking to see if anyone is transmitting. And if no one is transmitting over the spectrum at that point in time, then we can send data until there needs to be, that urgent primary user communication. So that's kind of the main idea behind spectrum sharing. And what it enables is this device-to-device communication. So on the right side, these are some examples of what device-to-device communication might look like. So traditionally, shown by case one, we have some cellular device that's connecting and communicating with a base station, for example. But in case two, these two devices, these two cell phones, if the frequencies that they want to communicate over are not being occupied by other primary users, then these two cell phones would be able to directly communicate with each other, essentially. And so this can take on a lot of different forms as well. That's kind of the simple case, but this technology can also be used to extend coverage from this base station to some device that might be out of the area or out of the network coverage range. And these devices can also be in the form of something like smart cars that are able to directly communicate with one another, whether or not they're covered by a particular cellular base station. So there's a lot of promise here in terms of having this communication without necessarily needing to be connected to the larger overall internet or the larger network. And so this is one example of how machine learning could be applied of, performing this intelligent spectrum sensing. And this is a type of resource management application. So the paper linked below talks a lot about the different areas where machine learning can be applied. Resource management kind of encompasses this spectrum sharing approach, but there are even other approaches that look into how machine learning can be applied for wireless communications, like networking, in terms of allowing the base station to manage its connections between different cell phones or people communicating with it, different ranges, mobility management. So that's the idea of managing the connection of a cell phone that's moving between different cell areas or base stations, and then also localization, which is using information about the RF spectrum to determine where exactly a cell phone or a device is with regard to just the environment in general. So resource management is our main focus for this particular study. And so diving a little bit more into the dynamic spectrum sensing problem, on the right side is a figure from GNU Radio that really visualizes this issue. So here in this setup, we have a QPSK, a quadrilateral phase shift keying constellation, right? So this is one of the ways that data can be transmitted over an RF spectrum. And so here, there are 4 different symbols that correspond to a particular bit combination. So you can think of a bit combination as 00, 01, 10, or 11, and that's the data that would be transmitted over the RF spectrum. Now, when these are typically transmitted, the ideal case is shown on the top left, where there's very little interference and very little noise that affects the in-phase and quadrature, so the IQ components of these different symbols. But as we enter some more real-world environments where noise and interference are just kind of a given, the IQ data points for those different symbols becomes increasingly harder to distinguish from one another. And as a result, the energy of the spectrum at those different points in times also becomes pretty inconsistent. So with this first case, it's pretty easy to tell how much energy one of these symbols is going to have. But in future cases where there's a lot more noise, it becomes a lot harder to actually pinpoint the exact energy that a symbol is going to have to determine if a spectrum is going to be free or not. And so that's kind of an overview of what the spectrum sensing problem is. How this can actually be tested and evaluated is using devices like software-defined radios, which is what we explore a little bit in this study. So software-defined radios are essentially devices that we can use to manipulate and control data that's being transmitted over RF spectrum. Essentially how it's made up is shown on the top right here. So there's a combination of an RF front end and a general purpose computing area. And so the RF front end is in charge of actually acquiring the RF data from the spectrum, from the RF frequencies, and converting that into a digital IQ representation. And the actual digital processing elements are going to be performing additional filtering or modulation and actually, using the data that the RF front end is collecting. So software radios are very flexible and very powerful and allow us to test things like the spectrum sensing demonstrations shown earlier. Some popular software-defined radios are Edis Research's USRPs. The Lime SDR is a recent one that's been announced, and also the RTL SDR, which is just a small USB dongle that allows you to plug it into the computer. And so essentially the main benefit of the software-defined radio and using this general purpose computing area is that we can do things like DSPs and machine learning acceleration, especially if this digital side of things is created using an FPGA, since we can pretty much implement that in hardware directly and process it without having to go through the software side of things in the computer. GNU Radio as well, I talked a little about it. It's a open source SDR framework that allows us to test these different software radio configurations. And there's actually a really cool framework called RFNOC, which allows us to integrate our custom FPGA, VHDL, or Verilog code and implement that on the different software radios, specifically Edis Research's USRP software radios, so that hardware accelerators can be used to test different accelerator applications. Like in this case that's shown on the right, a fast Fourier transform component was developed using VHDL and implemented in the actual FPGA of the USRP. So this shows a lot of interesting ideas for how we can, it's kind of building up, right? So we can see how we can actually create something like a neural network accelerator and implement that in a software-defined radio so that we can perform that spectrum sensing a little bit more efficiently. And that's actually not spectrum sensing, but modulation classification is shown as an example of using a actual hardware neural network core in the USRP developed by Edis. And so this is the software radio that we look a little bit more into seeing how we can perform this spectrum sensing. This is the Blade RF software-defined radio. Relative to the USRPs, it's low cost, entirely open source in terms of the FPGA architecture, so it's easy to modify directly. And it supports MIMO antenna, so multiple input, multiple output antenna arrays. On the right side, as shown in the picture, there are 4 different antenna ports using SMA, so 2 for receiving and 2 for transmitting. And it has a pretty decent bandwidth, and it's able to both have a full duplex transmitting and receiving, so it's able to do both at the same time. And it's supported by GNU Radio. But the only con with this particular software-defined radio is that it's not from Edis, and it doesn't use the Xilinx's FPGA, so it's not supported by RFNOC, which makes it a little bit easier to implement that hardware. But because of the other benefits, this was still an interesting SDR to work with for the research in this particular work. So just to break down the board a little bit more, the FPGA is shown in the middle, and on the right side is underneath the RF shield is the actual the RFIC, which reads the data from the antennas and translate that into the digital signals that are processed by the FPGA and sent over to the host computer via USB. And so getting into the actual research side of things, we demonstrated a couple of different implementations for how we can perform this spectrum occupancy prediction. The problem that we explored earlier with the delayed feedback reservoir, the network that we introduced with the single nonlinear transformation neuron, and GNU Radio first. So this is a GNU Radio flowchart, which is used to, just develop how data is filtered and processed using a software radio. So the process for just verifying and validating this idea is developed here. And essentially here we have I and Q data that's being read in from different files, for example. And the idea here is that we can send these IQ samples to a customized delayed feedback reservoir that's able to give us a binary classification between whether or not the spectrum is being occupied or it is free. And so this is just a simple flow graph that kind of shows that idea. And essentially we can see this happen in real time, the real-time classification of the IQ samples corresponding to the spectrum occupancy with GNU Radio. So after all the validation and software and the studying between the software-defined radios and the problem, we come to the main research question here, which is how can we develop this particular delayed feedback reservoir model in hardware for spectrum sensing? And we did 2 different approaches to actually realize this. The first was a mixed signal reservoir computing approach, and the second was an actual software-defined radio reservoir computing approach, where we incorporate that hardware onto the Blade RF itself. So first we explore the initial implementation, which is the mixed signal implementation. With this approach, we use a FPGA to communicate with an ASIC, and that combined realizes the hardware delayed feedback reservoir. So the system architecture is shown on the bottom left. The general idea here is that an ARM processor that's embedded inside of the Zinc FPGA on this development board communicates with the DFR that was implemented in programmable logic. So it uses the different registers and the AXI bus to configure the DFR and initiate the computation. And once that has been performed, the DFR executes those steps overviewed earlier to perform the inference. And to actually achieve the main idea here for the mixed signal part of this is that the nonlinear transformation, so that single node that was responsible for, passing this activation function code in the network, that's actually implemented in an external ASIC. And the reason for this is because the activation function of a neural network is typically what's going to use some of the most resources in terms of how it's actually implemented. So you can imagine that the matrix multiplication is one thing that consumes a lot of resources, but often what's not really considered is the activation function itself, depending on which one you use. And so these activation functions can take on the form of different architectures like hyperbolic tangent or sigmoid are two popular ones, or ReLU is another one. So instead of having to perform that complex nonlinear transformation in the FPGA, that was actually outsourced to the ASIC, and this was done using a digital to analog converter to first translate the digital data into an analog signal, feeding that analog signal to the ASIC, and then reading that back using an analog to digital converter. And that essentially is the entire flow for how this particular hardware implementation, this mixed signal hardware implementation, works. And so to evaluate this approach, we use two different benchmarks. NARMA 10 is a common benchmark for reservoir computing. And the second benchmark shown in the next slide is the spectrum occupancy problem that was discussed earlier. So with NARMA 10, this is one that was demonstrated in Jaeger's work, which was with the ESN, and also Appleton's work with the initial DFR implementation. The idea behind this is that we are generating some output samples, essentially. So this is more or less a moving average time series that's generated according to this equation below. So random inputs are generated in the range 0 to 0.5, and these inputs are passed into this function in order to generate the output wave, or the output time series that's shown in the top right. And so in blue is the actual expected NARMA 10 output, and the dotted orange line is the predicted DFR output. And this is typically measured, the performance of this is measured using a normalized root mean squared error equation. The particular equation that we used is shown at the bottom of this slide. And so with our hardware implementation, we found that it was able to achieve pretty comparable accuracy to what Appleton's initial DFR implementation was earlier. We also looked at another implementation of this hardware DFR as well and compared the accuracy to that. For the spectrum occupancy task, we used a data set that was provided by the University RWTH Aachen University in Germany. This is essentially a data set where some researchers had satellite or antennas on the top of a couple of different buildings and just recorded the RF activity for particular frequencies over time. And they used that and synthesized the data set by determining when actual devices were transmitting over those different parts of the RF spectrum and when they weren't transmitting. And so essentially that's kind of the foundation of the data set. And this ideal, or this realistic spectrum occupancy behavior, was essentially synthesized into those quadrature phase shift keying symbols. So over time, we generated that IQ sample data that corresponded to whether or not the spectrum was being utilized. And we fed that to the neural network so that it could determine and predict whether or not the spectrum was being utilized or not. And that was according to, the initial measurements. And so this was tested with a variety of different signal to noise ratios. And also in software, it was tested against a variety of different MIMO antenna configurations. So with this, you would expect the best performance, as shown on the right side, corresponded to an antenna count of 6. So the most antennas and the least amount of noise. How this data is measured on the right side is using a receiver operating characteristic curve. What this curve shows is the predictive performance of the model for a variety of different thresholds. So this is a very popular approach for measuring the binary classification performance of a network. And so what's shown is the idea behind the ROC curve is that the more square the curve is, the better the, or I guess the more robust the model is able to predict the different values for varying thresholds. And so the area under this curve is more so used as a measure of the actual performance for those different thresholds. So 1 is the ideal AUC, because that means that it was able to predict it across different thresholds. And so for the best case in this scenario with 10 dB noise, which is the lowest noise tested, and the 6 antenna configuration, the model was able to predict this information with an AUC of 0.913. So that was what we used to validate the actual hardware model and verify that it was actually able to perform the spectrum occupancy prediction well. Here I show a little bit of the actual characteristics of the hardware implementation. The most important thing here, I think, is the power dissipation. So it's shown here that the FPGA, the dynamic, or I guess the total power or the average power dissipation for the FPGA was on the order of 0.1 watts, which is roughly 130 milliwatts, was actually measured. So this was collected from Xilinx Vivato's tool. And the activation function, which would be expected to consume a lot more power, had even lower power consumption, right? So that was after we sent the data to the ADC, told the ASIC to actually perform that transformation and then read it back. And that's was the estimated power dissipation for that as well. Additionally, the actual utilization of the FPGA remained pretty low for this implementation as well. The highest utilization was found with the block RAMs that are the on-chip memories for the FPGA. The primary reason that this utilization is high is because of the way that the input data was being stored on the FPGA. So just for the initial test, all of the samples that needed to be classified were written into the FPGA, and then the host processor initiated the inference on the FPGA, and the output values were also stored inside of that FPGA as well. So this was the first kind of approach with seeing how we can actually perform this hardware spectrum sensing with this reservoir computing in FPGA. But there are a lot of limitations with this initial approach. One of the first things, and this is a pretty major issue, is that the signal integrity of the analog voltage measurements from the ASIC affected the accuracy of the model pretty significantly. On the right, I've shown a graph of some sample readings that we get back from the ASIC when we send, pretty constant input values to be transformed in a nonlinear way. So this is actually the ASIC, how it actually models, or the actual function that it's modeling is called the Mackey glass function. You can kind of see in general, the characteristics of the curve are represented, but there's a pretty decent amount of noise when we're actually attempting to read, individual data points back. So it's not a very continuous line; it's a very noisy line up until we get to 1.5, and the transformation starts decreasing, right? So this problem in general affected it affected the prediction accuracy for both of the tests that we tested. I think one of the ways that this can be resolved, which was not fully explored yet, is using the XADC averaging. So in this way, maybe we can have the output of the ASIC be a little bit more stable as we read it back, since we're averaging up to 256 different samples over time. Additionally, some other limitations of this approach are the design and verification time of the DFR core that was implemented on the FPGA. The main reason for this is because when designing this from hardware directly using VHDL or Verilog, you're prone to run into a couple of different issues. And also you have to go through the process of verifying this to ensure that it works in a variety of different states. And this essentially kind of limits the amount of time that you have to, go in, develop it, and test it. It pretty much impacts the amount of time that you're actually able to, deploy it on something like a software radio, for instance. And that kind of leads into the last problem as well, is the practicality of the system as well. In theory, the idea of sending this data to an external ASIC to perform the nonlinear transformation and then read it back into the FPGA is sound. But if we wanted to actually test this in real time using something like the Blade RF that we demonstrated earlier, it would be a little bit more challenging to demonstrate that because everything is on two different packages. So we have the FPGA itself, which is implemented on the Zinc FPGA package, and the ASIC, which is implemented in a separate package. But there really is no way to evaluate the ability of that ASIC externally to perform this spectrum occupancy on an actual software radio without designing a dedicated solution. So in the future, maybe designing something that incorporates both that digital and analog circuit side of things would be beneficial, but currently there wasn't really a good way to evaluate this system in that setting. And that's essentially what leads into the next part of this research project, which was exploring the actual implementation of the circuit on a software-defined radio. The approach that was taken to design this was a little bit different because it's resolving some of the issues that were found earlier, although there are some other things that might come up as a trade-off to the initial implementation. The first thing that was different with this approach is that high-level synthesis was used to create the actual delayed feedback reservoir core. High-level synthesis is an approach where we can take C++ code and directly translate that into hardware description language code, or HDL. On the right side, there's an example of this. So we have this initial component that's developed. Sometimes you might call it a DUT, for example, design under test. And the actual hardware that would get synthesized from this example is shown directly below it. So this is adding a variety of different different elements from a vector or from an array stored in memory to produce this output value B. And then that's the result that's returned. So high-level synthesis makes it really easy to generate and validate this different IP. And there are a variety of different optimizations that can be used directly to further improve the performance or efficiency of the hardware that's being created. And it circumvents a lot of the, I guess, design overhead that you would run into with manual physical VHDL or Verilog design. One of these optimizations that's shown on the right side is loop unrolling. So from this initial approach that's performed, if you synthesize this without unrolling, you would get the figure that's shown directly below it. But if you used an unroll directive in high-level synthesis, you could improve the latency of this hardware by reducing the computation time from 4 clock cycles to 1 clock cycle. And by taking advantage of this parallelism, you are able to, again, do this much faster, but at the expense of using a lot more hardware resources. So compared to the first approach, there are 4 different adders that are used in the unrolled approach. So even though you get a faster circuit, you trade that off with more area that's being used. And that's a common trade-off that designers are making when creating these different hardware implementations. It's a trade-off between parallelism and the actual area that's being utilized. There are a couple of other things that you can do with high-level synthesis as well that weren't necessarily explored too in depth with this particular research. One thing is you can do is memory mapping. So that's the process of actually, networking this IP that's developed to a bus. So something like Axie or Avalon, which is used in Intel, and have a host processor use this core as a dedicated hardware accelerator just in general. And also you can have this access external memory that's located outside of the core. So you could use that for things like reading weight values to perform this neural network inference inside of the core. So the way that this high-level synthesis DFR is used is shown in this figure. This is the Blade RF's architecture that we're interested in implementing the DFR core inside to perform the spectrum sensing. What's shown on the top is the RFIC circuit schematic, essentially. From the antenna, this RF data is being read, it's amplified and filtered out. And once that process happens, it's mixed to separate the in-phase data and the quadrature data. After going through more filters and amplifiers, this data is converted into a digital representation using the sigma delta ADCs inside of that chip. And then it's downsampled so that it can be now processed by the FPGA. On the FPGA side of things, with this software radio architecture, the samples are fed into a type of first in, first out queue. And the results from that queue without the IP that we have are then sent through this bridge that allows the data to be read by the computer. The idea for the modification here to perform this spectrum sensing in real time using the DFR is to implement this component right in the FPGA's programmable logic so that it's able to read the IQ samples from the queue, perform the spectrum sensing, and then provide the output prediction about the spectrum occupancy directly to the user that's using the host computer. The next slide here kind of explores a little bit about how the actual DFR spectrum sensor that would be inserted here is architected. The idea behind this is that the data samples are initially first stored in the actual FPGA. So it's in a non-real-time evaluation setting where we can read those IQ samples from this read-only memory, send them over to the high-level synthesis core, and store them in an output RAM that can be read by the user when they're ready to see the spectrum occupancy information. Eventually, a implementation that reads the data directly from the RFIC that was shown in the previous slide can be used, and this multiplexer can be used to control whether or not you're reading the data from the read-only memory that stores the static data or the RFIC that generates the RF data, the dynamic RF data for real-time spectrum sensing. This implementation uses quite a bit of logic in the FPGA. The reason for this is because we'll explore in future slides because of how some of the implementation aspects work. But compared to the initial Blade RF software radio architecture, there's pretty much a 60% increase in the ALMs that are being used, which are essentially the building blocks of the FPGA. The digital signal processors are all used here since we're using different floating point arithmetic. And also probably the least impact was on the block memory. So there's not a lot of data that's being stored in the actual high-level synthesis core. Most of the data is, most of these block memory bits are contributed from the initial Blade RF FPGA architecture. So testing this again, we saw pretty similar AUC. This was only tested with a 1 antenna configuration with a 10 dB SNR ratio. And the power for this was shown to increase pretty significantly compared to the previous approach. So this was on the order of 2.23 watts, which is still in the range of edge devices, but it's a lot more than that initial approach. In addition, there are a couple of other metrics that we measure in terms of the amount of inferences that could be performed per second with this approach and the maximum clock speed of the high-level synthesis core. So for this particular implementation, a lot was explored in terms of the trade-off between the different high-level synthesis optimizations that could be leveraged to improve the performance of the system versus, just exploring how those kind of affect the hardware in general. What we saw, just some things initially from testing this particular implementation, was that the input gain for the DFR, which is one of the settings that can adjust how much the input affects the inference prediction versus the feedback. We saw that there was a 60% better with lower input gain. So that parameter was kept pretty low versus the higher input gain, which was the max one that was tested was 0.9. So 0.1 was about the inference gain, the input gain that we specified here. And we saw that the feedback weight didn't have too much effect. So whether we varied that from 0.1 to 0.9, there wasn't too much an effect on that, on the actual ability to perform the spectrum sensing tasks in particular. More interesting is the actual hardware implementation. First, as shown on the right, the different aspects of the DFR were broken down based on the code that corresponded to those different functions. So with the DFR, it's the energy calculation, which combines the IQ data into one data point, the output accumulation, which multiplies and adds the data to the output prediction, the masking function, which is a part of the DFR as well, the Mackie glass activation function, and the process of sending the data into the network. So these are the different main functions that the DFR is executing. And what we found is that most of the lookup table utilization was affected, it was contributed due to the Mackie glass activation function. So in the mixed signal implementation, that was the thing that was optimized the best. But as you can see here, when that's actually implemented in digital hardware as a solid full block, it does utilize quite a few resources. Another thing that was explored a little bit was the trade-off between the loop unrolling that was explained a little bit earlier. What we found here is that loop unrolling for this particular implementation doesn't really affect the latency as much as it increases the power dissipation. So in this case, we increase the power by approximately 100%, unrolling the loop 3 times, but the latency of performing one inference on a single sample is only decreased by about 3%. So not a very fair trade-off, and loop unrolling doesn't really have much benefit for this particular implementation. 2 other features that were explored were the floating point precision and the actual effect of that on different floating point operations. So on the left is shown the different utilization of the logic elements for various floating point precision values. So most of the increase in this is shown thanks to the DSP itself. So coming off of here, so the spectrum occupancy prediction, it reduces by about 30% when we reduce it to 16 bits here, but it saturates around 26 bits once we go beyond this point here. So 26 bits was pretty much the sweet spot that we found for, the number of bits that were needed to perform this spectrum sensing with the best accuracy. So improving the floating point bits beyond this didn't really affect the precision of the model very much. Additionally, the DSP utilization was the number one thing that was affected, but the MLab unit utilization, which is the memory logic array blocks, were also impacted quite a bit, especially when we transition from 46 bits to 56 bits. On the right side, a little bit of the reason for this DSP increase was explored. Primarily, the main contribution of this high DSP utilization was due to the power function, and this is what was used in the actual Mackie glass function. So the power operation that occurs between these floating point numbers, it increases pretty significantly, almost 100% when we're transitioning from 46 bits to 56 bits. So this is the primary reason why during the transition from 46 bits to 56 bits of precision, the DSP utilization increases by so much. So that kind of overviews a little bit about how the 2 different ways that we implemented these reservoir computing DFRs for spectrum sensing worked. Now we'll explore a little bit about the trade-offs between the 2 approaches to conclude. So the high-level synthesis approach, which we just demonstrated, it's very accessible, and we can easily modify the logic so that this can be adapted for a variety of different applications. It's very easy to test this, since the C++ code is able to not only generate the synthesizable logic, but it's also able to generate a test bench that can be run in Model Sim to verify that it works okay with the hardware implementation. Furthermore, actually implementing this in a software-defined radio to record the performance and test it in real time is very easy, since all of this is happening within the FPGA itself. Again, the only main downside of this approach are the multiplication and power operations that have to be modeled in hardware to achieve the particular activation function that we looked at for this approach. This can be resolved a little bit by using lookup tables instead of manually hard coding the particular activation function using dynamic logic like DSPs. This would, of course, lead to more increase in the memory utilization of the FPGA, but it is also another interesting avenue to explore. Alternatively, the mixed signal DFR achieves a lot lower power consumption. It requires a lot less energy to actually execute, and the area is much smaller, aside from the approach that was used to initially store the input samples. However, the trade-offs with this is that we have to use the ADC and the DAC to send data back and forth between the ASIC, and this can lead to a little bit more power consumption and use more area. The noise of the actual ASIC itself when testing it in real time and seeing some of those results affected the accuracy quite a bit. So that's also one of the major downsides for that as well. And also it's not as practical to get this up and running in a realistic RF setting, such as on a software-defined radio. So I'll conclude with the main contributions of this particular research work and a little bit about the significance for why this research was important. So the main contributions, again, we developed a mixed signal delayed feedback reservoir and demonstrated that for an FPGA ASIC platform in that hybrid setting. We demonstrated the NARMA 10 performance of that system and the spectrum sensing performance of that system as well. And in addition to the mixed signal approach, a high-level synthesis approach was developed as well. So this was utilized using Intel high-level synthesis compiler. It was implemented on the Blade RF software-defined radio inside of its Cyclone 5 FPGA. And the results for spectrum sensing were verified using that embedded read-only memory where we classified the different IQ samples based on whether or not the spectrum was free or occupied. And finally, this was made pretty much available so that future research and development that continues off of this, whether it's looking at the hybrid circuit approaches for using Xilinx's Zinc XADC and DAC to perform that communication with an external analog circuit, or the actual high-level synthesis approach and seeing how to incorporate that on the Blade RF software-defined radio. All this was documented on the GitHub repositories for these, which are shown at the bottom. And I think this is kind of an important thing to mention as we go over to the significance. It's kind of overviewing that as well, because there aren't really a lot of resources that have really explored why or how we can implement these different types of accelerators directly in the fabric of contemporary software-defined radios. RF NOC is one approach that is attempting to popularize it, but there still needs to be kind of more examples to demonstrate this, not only with Edis Research software-defined radios, but also with various other software-defined radios that are out there. In addition to just contributing and making more examples of this approach available to further research and development for software-defined radios. It's also one of few approaches that shows the advantages of using an external activation function in an ASIC, which it can be a lot lower power and easier to implement in hardware versus having to implement these activation functions in digital logic. The combination of, again, demonstrating these reservoir computing techniques with software-defined radios and in hardware is something that's still being explored a little bit more, since reservoir computing hasn't been as popular as the LSTM and the GRU approaches that have been shown earlier. So that's another kind of key thing demonstrated here. And also the analysis of what the high-level synthesis tools are actually doing when these are used to generate the logic is also important. Because again, this is something that's not too frequently used, at least mentioned in a lot of the contemporary FPGA research that is being published. So having more examples of how to implement these different circuits using high-level synthesis and evaluating the performance of those implementations is something that would be beneficial to document a lot more in these studies. So this concludes the work that was done for this research. In terms of future works and what's next, a lot of areas of this project can, of course, be approved. The first area that I think can be immediately applied to this is using more of those optimization techniques that were demonstrated in the paper covering the hardware ESN that was mentioned earlier. So time multiplex networks pretty much covers, I think, a lot of the main advantages for those optimizations. So folded in time networks and this idea of one neuron architectures has a lot of promise in terms of hardware simplicity. So exploring those architectures could be beneficial, and also exploring on-the-fly weight generation, as well as binarized and quantized weights to reduce the amount of memory that's used and reduce just the computation that's required in general, also can be promising in terms of reducing, a lot of aspects in terms of the overhead of these machine learning circuits. Finally, backpropagation can also be used to improve the accuracy of this particular models a little bit for some of the applications that we tested. An exploration of spiking versions of these DFR networks would also be beneficial as well. Not too many works have, if any, have shown the implementation of these spiking neural networks on software radios. So this essentially kind of sets up the idea for putting this network on the software radio. So converting this into a spiking network, which would be likely able to reduce the energy required and the area occupation of the circuit, would be beneficial to explore. Some of the other advantages of that are fault tolerance, which doesn't so much apply in this particular case, since there are very few neurons, but in terms of larger SNN implementations that could be implemented in hardware, that is definitely one of the advantages as well. And also looking at how this can be done using some approaches like ANN conversion, or even just directly training the spiking neural network using approximate or surrogate gradient descent and spike timing dependent plasticity, which are two of the most popular ways that ANN or SNNs are trained. Finally, testing this against more sophisticated applications outside of the spectrum occupancy task would be very beneficial to show, and can be relatively easily done once the actual network implementation on the software radio has been refined to a point where it's being able to be tested in real time. So applications like specific emitter identification, where a user can determine who exactly is transmitting a signal just based on artifacts of the actual transmission or the transmitter hardware. Modulation detection, determining which particular modulation is being used to send data over an RF network. Indoor localization, so pinpointing exactly where a device is relative to an indoor location, since GPS is known to have a lot more issues pinpointing devices in indoor settings. And also symbol detection, which can be used to determine what type of symbol has actually been transmitted over the RF channel. Furthermore, I think the exploration of actually demonstrating this using RFNOC, maybe on an NS Research USRP, could be beneficial as well, in addition to exploring maybe some actual ASIC implementations and demonstrating, which might be able to better show the mixed signal implementation that was proposed as the first part of this work. So these are areas that I think could further improve the quality of some of the research projects presented here. And I think that actually concludes the presentation. So thank you all for your time, and I'll take any questions now if you have them.
Well, I have one, I guess, maybe kind of big one. Could you put slide 37 back for a minute?
Absolutely.
I mean, I'm convinced the work is there. I mean, I don't want this to come across, but if you look at the conclusions and contributions and significance, a lot of those look like project words. Like, I did this, I explored this, I went off. And the thesis read that way as well. I was kind of hoping for it to be a little bit different in the presentation. I'm convinced the work is in here, and this is kind of something that can be maybe reframed, but I don't see the hypothesis. I don't see, the big problem, the more focused problem, the hypothesis. I'm going to show you how I'm going to investigate that so that you understand the results, and then the results. That's the typical thesis. So it's in there. I believe it's in there, but I need to see, and I hope that in the thesis, some of that could be reframed in the abstract, the introduction, and the conclusion. Really, just why are you doing? What results do you hope to show? What are you exploring? Why are you doing this? That's what I think needs to come across a little bit better. And let me just say, I think the work is there. The understanding is there. I don't question that at all. It's really just the typical thesis way of saying things, which is, why am I doing this? Why will it be a contribution if I do it?
Yeah, thanks for your feedback, Dr. Paul. That's a pretty good advice, and I definitely do want to make that more clear. So I want to hear a little bit more about your feedback after this so that I can refine the thesis a little bit more to make that more clear. I guess
I'm sure you can do it. I have no doubt. I'm not questioning that at all. So I just want that to be clear, because it's quite clear. You know, I looked for it the whole time you did the presentation. I thought maybe the presentation would frame a little bit differently, but it really doesn't. It frames it kind of the same as the writing. And I know it's in there. It's just not stated boldly, clearly, that type of thing.
I understand. Okay. Yes, I'll definitely make that more clear. And I will say that this was primarily an exploration of how exactly is the best way to implement these different reservoir computing networks in FPGA and in software-defined radio hardware. So it's more.
Yeah, but you had a thesis as to why that was worth exploring, and that doesn't come across. Why are you doing it?
I gotcha.
I mean, it comes across as a very classic local versus remote computing problem. They've been around for decades, right?
Mm-hmm.
And there's always trade-offs there. So you have those trade-offs. There's a slide there, you know, there's discussion of that. So those trade-offs lead you to explore these things towards a purpose for that exploration.
I understand.
And that does not come across. What really, if you look in your thesis, it says, well, we looked at this stuff because it's good to look at. That's really the way it reads. And it can be a lot better. It should be a lot better.
I see. Okay. Yeah, just to summarize the main idea, and I'll definitely clarify this a lot more in the actual thesis paper. But the main significance why this was important to look at is really due to the simplicity of the model. So just really demonstrating how a simplistic model for performing these spectrum sensing and spectrum occupancy types of tasks can actually be implemented.
It was in there somewhere too that you're trading off accuracy, right? That was in there.
Right, exactly. Yes.
And so you're saying that it's worth it.
Yes.
You're saying our thesis is that it's worth it for reasons A, B, and C to trade off this for this.
Right, exactly.
That's what's missing.
I gotcha. I understand.
And so in order to be able to accomplish that, we did A and B. You did basically two broad areas. And when we're looking at this, we're going to look at, you know, X and Y in order to show you that this was worth doing or not. It's actually perfectly valid if you find that it wasn't, you know, as long as you went off and did it, then, you know, did the experimentation. But but that's the part that concerns me. And if you look at these words, they really look like project words. They don't look like thesis words.
Okay, I see.
But again, let me just say, I'm convinced the work is there. I would have a couple questions about things like, you know, why you didn't get more benefits out of the loop unrolling. I'm kind of curious about that, but I really do, you know, the work is clearly there.
I understand. Okay.
Yeah,
Any other? Oh, okay.
A suggestion from Professor Paul's comments. So I think in Osaze's work, including the thesis and the presentation, you spend a lot of time talking about the details, what you have been done and how you analyze those data sets. That's good. But also you need to think from the big picture. Think about why we needed to use neuromorphic computing instead of still using the traditional von Neumann structures. So this is what Professor Paul is emphasizing. Like think in the big picture, like what kind of contribution you have for the whole society, like for the computing society. Mainly the neuromorphic computing is for energy efficiency. That's the first benefits you can get. And you are actually the first one using both FPGA and ASIC co-design platform to design the reservoir computing. So that's the biggest contribution you have in your work. So maybe you need to emphasize that in your abstract and the introduction in your thesis.
Okay, that sounds good, Dr. Yi. Yeah, thank you for clarifying as well.
Oh, no problem.
This is Cameron. When I looked at your thesis document, I assumed the main contribution was going to be a comparison of the combination of an FPGA and a analog ASIC versus a purely digital implementation, and you do that. However, and you compare the two as well, but they are fairly different, both in terms of the vendor and their tools. And so I'm just curious how strongly you find the comparison to be, or the accuracy of the comparison to be. There are you're using high-level synthesis, that's state of the art. However, I have used both Intel and Xilinx high-level synthesis tools in past projects. This was some time ago, but found the Intel tools to be not able to produce as good a results. Perhaps that's changed. In fact, in your discussion, you point out in terms of resource usage, it's primarily due to various floating point operations like the power function. The HLS tools typically just make use of a floating point core, a very general purpose core that is parameterizable in terms of the size of a floating point word, and is able to implement a variety of functions, arithmetic and other things. So in a sense, that's not really too different from what a processor is doing. Processors have floating point cores that are capable of various operations. So I'm just curious your comments on that, how optimal you think you have been able, how much optimality you think you've been able to achieve. I should point out that there is another floating point core generator that has slightly different implementation. It's something called Flopoco. It's open source, been around for 10 or more years. You can actually generate your own operators, and it academics have been using it for a while and often get better results. It's able to optimize across operations, and I'm just wondering if that might improve your results.
Yeah, those are all very good questions, Dr. Patterson. It sounds like most of the question that you've asked is in terms of one of the main things you asked was the exploration of the different ways of optimizing and whether or not this is truly the most optimized version of the DFR core using Intel's high-level synthesis, since it is using, a lot of those DSP blocks, which, as you say, are very similar to the general purpose computing approaches. And I will say that I haven't been able to explore all of the different optimizations that Intel high-level synthesis compiler has to offer. There are still a couple of ways that I think that using Intel's tool, that this particular core can be made even better. Definitely by far the number one way is by substituting the activation function, getting rid of some of the power operations and instead replacing that with the lookup table to provide a much more fair comparison between the mixed signal and this implementation in particular. In terms of the actual DSP utilization, that was mostly I left up to Intel to decide, the compiler, but there are switches inside of the high-level synthesis compiler that you can use to manipulate to which degree it's using those DSP blocks versus the actual lookup table logic, the programmable logic. So that's something that can definitely be explored as well to better understand the power and the area trade-off if maybe some of more of those modifications are used, in addition to like some of the directives that they have that can also be that can also improve things like the loop, which was attempted to unroll.
I'm just curious. Maybe there were constraints that I just am unaware of, but in the beginning, was there any goal made of trying to create a common platform that would enable you to just more fairly compare the ASIC versus the digital version of everything?
Not in the beginning, no. Yeah, so that was kind of an interesting comparison that I wanted to make as I was in the middle of developing the actual HLS DFR core. But I think that, as you say, that definitely would make a little bit more of a fair comparison between the two approaches for this common task.
Well, it's two classic comparisons, right? FPGA versus ASIC and digital versus analog. So I think you've given some insights into that, but comparisons have to be fair. And so I'm just curious how much you're standing by the comparison, and as providing insights into these different ways of doing things.
Yeah, I agree. And I think some of that would be addressed in the problem statement a little bit, like this is what we're looking for.
Okay, I see.
So at present, it comes across as, well, you can do it this way, or you can do it this way. However, maybe a little more guidance for which way, since power seems to be a major consideration, and interfacing to external chips is inherently, incurring quite a power hit. I think you could say it's future work, but I would expect a good number of people are very interested in that, in the guidance you can provide for that way of implementing these different ways of implementing it.
Right, I understand.
Yeah, keep in mind, you really only need to show one thing to make it a contribution. Everything else is sort of what you did in order to get there, right? So it's almost like sometimes the more contributions a thesis has, the less it has. And when it has one, and then it has a lot of things that you did to support that, then you go, oh, there's something there, and this is what they did. They did all this stuff to get to that one main contribution, and I actually think it is in there, but it's not coming across.
That's all. Thank you.
Okay, thank you for your questions, and thank you for the suggestions as well. Are there any other questions from the audience?
Oh, I don't.
Yes, I do. So actually, Osaze's work concluded two parts. One is actually using the FPGA and the ASIC to.
I think you muted yourself, Dr. Yi. Okay.
Yeah, the delay feedback reservoir computing system. So my first question is related to the first part of your project. So why you choose DFR instead of echo state network? Is there any specific reason?
Right. So the main reason for choosing to explore the DFR architecture is primarily due to its simpler architecture. So as shown in this work, Appleton's work, which is kind of the basis, I'd say probably one of the first works to demonstrate this idea of a single neuron network, wherein that one neuron is artificial neuron and it has the activation function, and the others are these virtual neurons. The idea of using this simplified version and instead just time multiplexing the network leads us to a lot lower hardware complexity compared to the echo state network, which I show here, wherein we can have a lot of neurons, but all of those neurons are going to incorporate their own specific activations, right? And so the main advantage for using the DFR versus this echo state network is in its simplicity, since it carries over some of the advantages of the echo state network while also removing some of the complexity in this initial reservoir by reducing the number of artificial neurons that have to be leveraged.
Okay, good.
Yeah.
So, sorry. My second question is actually related to the second part of your project. So when you're trying to apply it to the software-defined radio, you use HLS the most. So did you meet any difficulties when you use HLS? I know HLS is easy to use compared to write the Verilog code, but still, when students use HLS, they met difficulties. So I would like to know, like, what kind of challenge and the difficulties you met when you use HLS?
Yeah, that's a pretty good question. I think the primary challenges all related to just using the tool itself. So programming in C++, that's kind of a given, but learning about the different ways that the tools, optimization techniques can be used together to improve the design, I think was one of the challenging things trying to figure out about it. So for instance, you can execute the power function with different precision for floating point numbers in the high-level synthesis tool. But when you want to change that to the floating point the fixed point representation, which allows you to control the bits a little bit more finely between the actual decimal bits and the integer bits, and then creating the power operation for that, it wasn't as intuitive using the tool how to go about implementing that with your own custom floating point types, or if that was even possible. So I think being able to explore the different varieties of quantization and the different types of quantization was a little bit tough using high-level synthesis, and that was, I think, the main challenge. Perhaps the other challenge was looking more into the loop optimizations, since that's the other primary benefit that the tool offers in terms of what you can do to realize this code. So there are a lot of other optimizations that I wasn't able to fully explore in depth, and their impact on the hardware that was generated, like declaring the loops as exclusively independent, and some other things like improving the latency or the pipelining degree of the different loops. So recording the performance of those different loop optimizations and really exploring how they affect the generated design is another thing that was a little bit difficult to do. But in general, using the tool itself is pretty straightforward, and how they actually combine all this stuff isn't too bad to use. Yeah, it's just a matter of trying to explore some of those particular things with maybe a particular implementation that was a little bit difficult.
Mm-hmm.
Yeah.
It's not
Hopefully
hard to use, but I guess the loop unrolling didn't really work.
Yeah,
right.
exactly.
I mean, it's
Yeah.
easy to do, but doesn't do much.
Right, exactly. So, and that's exactly kind of my point, like learning how to kind of work with the tool, which is generally like the main, I guess, challenge in this era of digital design, is like learning how to work with the tools and get them to provide what you actually want them to provide, was the challenging part of using high-level synthesis, right?
Yeah, that's true. Mm-hmm.
Well, it does tie together some of what you've spoken about. NVIDIA is a power user of high-level synthesis. They simply wouldn't be able to meet their release schedules without using it. And in our experience, if you're doing floating point work, HDLs, you can simulate floating point arithmetic, but very few of the tools actually will synthesize floating point calculations, whereas HLS is just will do that for you. So, I think it was an appropriate choice for what you're doing.
Yeah.
All right. Thanks.
Yeah. Thank you. Thank you.
Yeah, thank you. That's all my questions.
Thanks.
Any
Alrighty.
questions from the students? Okay, so if there is no questions, we will put all the students, please leave the meeting, and I will put Osaze in the waiting room so all the committee members can discuss about Osaze's master thesis work.
Alrighty. Thank you all for joining.
Yeah, so please stay in the waiting room, so I will let you back.
Good job,
Alrighty.
Osaze. Good job.
Thank you. Let
Thanks,
me
Juliet.
stop.